Okay, so I think we are all here. Thank you everyone for joining the tutorial for human-centered explainability for healthcare. We have an exciting lineup all throughout. The videos have been already posted in our workshop room, and we will be sharing our slides on the workshop webpage after the tutorial. This live stream will mainly happen so that we can play the videos in real time, take your questions and answer them as it comes out. As I was pasting on the Zoom chat, please just use the Zoom chat for the duration of this tutorial. We will be monitoring this chat and we'll be answering these questions as either via chat or we can even like bring them up. So I would just take this opportunity to introduce you to our tutorial panel. Many of us are present here. A few of us will be joining probably over the course of the day. So I can start with first myself. I'm Prithwish Chakraborty. I'm a research staff member at IBM Research, and I'm very excited to share this tutorial with my colleagues from IBM Research. Um, let's see. Amit, do you want to go next?
Sure. Hi. Hi. So yeah, I'm Amit Dhurandhar. I'm also a research staff member at IBM TJ Watson. And the last few years, my focus has been on explainable AI in particular, and to some degree also other things such as causality and quantum computing and so on and so forth. So happy to be here. Thank you.
BC, do you want to go next?
Hi, can you hear me?
Yes, we can hear you.
Hi. Hi, thanks for the introduction. My name is Chul Kwon, but I go by BC, and I'm really happy to be part of this tutorial. I'm also a research staff member at IBM Research here in Cambridge, Massachusetts. And my research focus is to use the visual analytics methods to investigate the healthcare data for healthcare problems. My focus is to use experts' knowledge and integrate the knowledge with the machine learning methods using intuitive, interactive visualizations. Hope you enjoy the tutorial. If you have any questions, feel free to post it on the chat or reach out to us. Thank you so much.
Great. Daby, do you want to go next?
Sure. Hi, everyone. So my name is Daby. So I'm principal research staff member, also from IBM Research in Yorktown. I do also have some management responsibilities. Overall, from a research perspective, the focus is on disease progression modeling, predictive models in healthcare. And as you can imagine, explainability for such modeling is very, very important. And I'm very happy to be here as well. Thanks, Prithwish.
Kenney, do you want to go next?
Sure. Welcome everyone to the tutorial. My name is Kenney Ng. I'm a principal research staff member at IBM Research. I also manage the Health Analytics Research Group. Both my team and I are based out of Cambridge, Massachusetts. Our primary focus is on the development and application of machine learning and AI to real-world healthcare to improve patient outcomes. We hope you enjoy the tutorial. Thank you.
Sanjoy?
Sure. Hi, my name is Sanjoy. I am a research staff member at IBM Research here in Yorktown Heights in New York. My research interest is mainly on applying machine learning and healthcare AI techniques on healthcare data. Welcome to the tutorial, and I'm pretty happy to present along with my cohorts. Thank you.
Great. So let's start the tutorial. As mentioned before, feel free to post your questions on the chat. We will either be answering them on the Zoom chat or pausing the play and addressing that with all of our panel here. Great. Let me start sharing the tutorial.
Hello everyone, my name is Daby. I am a principal research staff member and manager at IBM Research, and on behalf of my colleagues, Prithwish Chakraborty, Chul Kwon, Sanjoy, Amit Dhurandhar, Gruen, Kenney and Kush Varshney, I welcome you to this KDD 2020 tutorial on human-centered explainability for healthcare. So this is a 3.5-hour tutorial with a 30-minute break in the middle. We will start with introductory comments motivating the need for explainability in AI systems for healthcare before spending some time to level set everyone on the state of the art in explainable AI, including a deeper dive on a curated set of relevant techniques for healthcare problems. We will then spend the rest of our time together here on healthcare and user requirements for explainable AI before diving into concrete use cases for key stakeholders within the healthcare ecosystem, namely the data scientists, the clinical researchers, and the clinicians. Okay, on to the first part of the tutorial. Let me start this introductory motivation with general observations on AI and on AI in healthcare. So from a business perspective, the market for AI in healthcare is projected to expand significantly. Today in 2020, it is evaluated at approximately $5 billion with a very significant projected growth, varying from $27 to even $45 billion by 2025, depending on the source, and with very, very significant compound annual growth rates. In some cases, we're seeing one of almost 45%. So no matter the source, the business potential is enormous and driven by specific needs by this industry to reduce costs while improving outcomes by leveraging the growth in the amount of health data available that is being collected, as we will be discussing further in this tutorial. So this data availability has fueled the academic community to innovate significantly and accelerate this pace. These two charts show the exponential growth in terms of number of PubMed index publications in ML, machine learning / AI over the last few decades. This is a snapshot taken in March of this year. While this should not be a surprise to this audience, these graphs do show that the uptake of AI in healthcare within the academic community has grown exponentially during the last couple of decades. The range of applications of AI in healthcare is actually quite large. From a provider perspective, we are witnessing the development of models helping understanding how disease progress, models able to estimate risk for complications, prediction models of adverse events, for hospital readmissions, and so on and so forth. We are also witnessing the development of analytics for decisioning, aiming at estimating the impact and effectiveness of specific treatments, typically using causal inference techniques. From a payer perspective, AI is being used to develop outcome-based payment models to handle authorization issues or even insurance fraud. That's actually a very, very prominent area of focus by the payers. From a pharmaceutical perspective, AI is very much used to speed up, for instance, drug discovery, a need that is really exacerbated these days with the current COVID-19 crisis. AI and causal inference is also researched to figure out how to emulate and speed up clinical trials from observational data. Post-market surveillance and pharmacovigilance, once a drug is launched, is an important area of focus, seeking to develop computational techniques to detect from real-world evidence, can we detect if a drug is causing adverse reactions? Last but not least, from a patient perspective, AI is also having an impact. With the advent of IoT, end users have access to lots of wellness and healthcare apps collecting data with sensors on themselves. There's also a plethora of applications for the management of chronic disease that are appearing, diabetes being one example. Access to trials with proper matching is another area of interest here. Most of these examples are benefiting heavily from progress in ML, machine learning, and deep learning. Healthcare data has its own characteristics in terms of sparsity, biases, incompleteness, noise levels, etc. And the community has been developing and extending machine learning and deep learning techniques, or in some case even reinforcement learning approaches, together with causal inference and other statistical approaches to cope with these challenges and push the envelope for providers, payers, farmers, and patients. So despite all this hype, the academic uptake, data availability that has increased, and these tremendous business projections. So despite all of that, some aspects of that growth are still quite underwhelming. In fact, AI as a whole is booming, but there are signs pointing to a slower than expected adoption of AI systems. The top left chart shows aspects of a Gartner article showing that in 2018, 23% of AI systems were supposed to be deployed within the next 12 months, while 14% were already deployed in 2018. Fast forwarding to 2019, and we see that these 23% did not materialize. In fact, only 5% from 14 to 19% are reported in this report. And what are the hurdles? Well, quite a few things. The first one that's reported here points at this a skilling problem with the staff. There are data quality issues that are emerging, and also a general problem, which is really what we're focusing here in this tutorial, is what they call the fear of the unknown, in terms of understanding how the AI benefits and its uses. So end users are not always comfortable and ready for adoption with that fear of the unknown. Last year, the White House produced a report. This is a report by the Select Committee on Artificial Intelligence of the National Science and Technology Council. Highlighting in this report is the need to provide more explainability and transparency on AI systems, citing the opaqueness of these deep neural nets and how this is hindering the adoption in fields like healthcare, where decision makers need to have some handle on what the AI is doing and how the AI is arriving at its conclusions. The slow uptake of AI in general is definitely a reality in healthcare as well, with numbers provided at the bottom left of this chart. We know that it is coming, meaning AI in healthcare is coming, but there are concerns that are hindering its use. And this slide also highlights the same fear of the unknown concern reported within the health IT community in this case. So here we have, for instance, a Harvard Business Review article citing the black box nature of AI system as a problem for adoption. Another article here from Healthcare IT News talks about the lack of trust as a hurdle to overcome for widespread use of AI in clinical settings. This need for trust is further highlighted in these articles shown in this chart. So the Harvard Business Review article at the top left has quite a provocative title as a question. AI can outperform doctors, so why don't patients trust it? Addressing this trust issue is also linked to medical ethics issues all the way up to the Hippocratic Oath. The Forbes article on the right-hand side has some interesting questions in its body. For instance, what happens when an AI system makes the wrong decision? Who is responsible? So while the healthcare community at large is posing these very, very important questions and seeking answers, explainability in AI has been gaining a lot of steam, and it's actually being recognized in some cases as its own research area with workshops that are emerging. So despite that, we believe that there is still a gap that needs to be filled between the rather low-level explainable AI methods, low-level in a sense of the type of insight that they provide, as we're going to see in the rest of this tutorial. So we believe that there is still a gap between that and what an end-user stakeholder, maybe a clinician, even eventually a patient, would want to consume. So this tutorial addresses aspects of this gap by looking at explainability from an end-user perspective. So before turning into methods and concrete use cases, let me pass the baton to my colleague Kenney, who will go one level deeper into AI adoption challenges in healthcare. Thank you very much.
Hello, my name is Kenney Ng, and I'm a Principal Research Staff Member and Research Manager in IBM Research Cambridge. In this section of the tutorial, we will focus on identifying some of the main challenges for adoption of AI in healthcare practice. Many AI healthcare models have been developed and demonstrated to provide value in research, demonstration, and prototype settings. However, the adoption, deployment, and use of such AI models in actual clinical practice has been slow and remains challenging. There are a number of reasons why this is the case. At a high level, it all comes down to trust in the AI models. In more detail, the reasons include challenges related to explainability, bias and fairness, robustness and compliance, data privacy and data quality, and alignment with existing clinical workflows. We will discuss each of these issues in more detail next. What is trust? According to the Merriam-Webster Dictionary, trust is the assured reliance on the character, ability, strength, or truth of something. Trust cannot be demanded. It needs to be earned. From repeatedly using the system and having good experiences and consistently getting something useful and helpful in return. On its own, this is already a very challenging task. However, we have even more work to do since we need to also overcome the existing negative attitudes towards AI in the popular press. Here are some recent headlines that illustrate some of the trust issues that we face. The Economist has a story that says, "Don't trust AI until we build systems that earn trust." The New York Times reports that many facial recognition systems are biased. Recently, large technology companies such as Amazon, Microsoft, and IBM are slightly social distancing from the $8 billion facial recognition market, as reported in Forbes. A Science article highlights adversarial attacks on medical machine learning, raising concerns of AI reliability and robustness. And a story from Stat from a few years ago, reporting that the IBM Watson supercomputer recommended unsafe and incorrect cancer treatments, still casts a cloud over IBM. As you can appreciate, we certainly have our work cut out for us. First, we look at explainability, which includes aspects of transparency, understanding, and reliability. The question that needs to be answered here is your AI transparent? More specifically, the user needs to know what data and information was used by the model. How did the model arrive at the result? How applicable, confident, and reliable is the result to a specific patient of interest? Later in the tutorial, my colleagues will discuss a number of methods and approaches related to various aspects of explainability. Here, I just wanted to highlight two proposals that are steps in the right direction to improve explainability of AI models. One is the transparent reporting of a multivariable prediction model for individual prognosis or diagnosis, or tripod statement, which is a checklist of 22 items that tries to improve the reporting of prediction model studies. The other is a model facts label that provides information so that clinicians know how, when, how not, and when not to incorporate machine learning model outputs into clinical decisions. Next, we turn to bias and fairness. The question that needs to be answered here is your AI unbiased and fair? AI machine learning, by its very nature, is always a form of statistical discrimination. The discrimination becomes objectionable when it places certain privileged groups at systematic advantage and certain unprivileged groups at systematic disadvantage. Bias and unfairness can be caused by data, model development, and model deployment. In particular, the user needs to know Does the AI model behave appropriately for subgroups of the population? Are there subgroups that are systematically advantaged or disadvantaged? Here are some relevant recent headlines. An article in Nature cautions that without careful implementation, AI could widen the healthcare inequality. In a Science article, racial bias is analyzed in an algorithm used to manage population health. In a recent New England Journal of Medicine article, clinical algorithms with race corrections were evaluated and shown to potentially cause unintended biases. Next, we turn to robustness and compliance. The questions that need to be answered here are, is your AI robust and secure? Is your AI governed appropriately? Related to robustness and security, the user needs to know that the model is operating properly and that the model has not been tampered with. Related to governance, the user needs to know that the system is following the established healthcare regulations and that there's a process for auditing and human review in case some issue or problem is discovered. Next, we turn to data privacy and quality. The questions that need to be answered here are, do you have rights to the data? Is the data reliable? On the privacy front, we need to assure users that we have followed the appropriate rules and regulations, such as HIPAA and GDPR, and that we have access to the appropriate data needed to train the model. On the data quality front, we need to convince the users that we are aware of and able to handle the challenges related to interoperability, noise, sparsity, and missingness. We need to avoid garbage in, garbage out scenarios. Finally, we turn to issues related to alignment with existing clinical workflows. The question that needs to be answered here is your AI easy to access and use? We are all aware of the problem with physician burnout caused by the confluence of several issues, including low control of pace, chaotic environments, time pressure, family responsibilities, and electronic health record or EHR systems. The top 5 EHR burdens reported by clinicians include less patient engagement, extended workdays, quality measure demands, poor design, and cost and maintenance. To encourage the adoption of AI in healthcare practice, there has to be seamless integration of AI models into the existing clinical workflows. The AI needs to help the clinician work smarter, not harder. The AI needs to present insights intelligently back into the workflow. In other words, the right information at the right time in the right place. The AI needs to let clinicians focus more on the patient with the confidence that better data is helping them provide better care. In summary, in this section of the tutorial, we identified some of the main challenges for adoption of AI in healthcare practice. Next, we will look into explainability in more detail.
Okay, that brings us to the end of the introduction section. I'm going up the next part. If you have again any questions, please feel free to use the chat now. Thanks, Kenney. Hi everyone, I am Prithwish Chakraborty, a research staff member at IBM Research. Till now, we have heard about the promise and the challenges of AI in healthcare and how it is inherently tied to explainability. To better situate our tutorial, I will now take this opportunity to walk us through a healthcare specific use case. So the use case that we are going to look at today is about medical expenditure prediction from survey data. This dataset was made publicly available by AHRQ. The elements include demographic factors such as gender and age. It also contains socioeconomic variables such as income, as well as medical conditions. These medical conditions comes from self-reported summary from the patients themselves. Typical consumers of such predictions can be healthcare payers, as mentioned by Daby a few slides before. Our goal with this use case is thus to model such expenditure patterns and investigate the factors that can lead to high expenditure and so on. So one of the key tasks while going on any such use case is to take the decision as to whether we should build a directly interpretable model or rather focus on performance and perhaps build the best black box model and think about post hoc explanations at the end. We will explore such considerations and perhaps some guidelines towards the latter part of this tutorial. For this particular use case, we are going to build a directly interpretable model. Coming to the dataset, so as I mentioned before, this dataset was made publicly available by AHRQ. It contains 2 years, 2015 and 2014. And to use the dataset, we are going to use AIX 360 package. The link to the example tutorial notebook is present in the slide. AIX 360, as we will stress upon in a few minutes later, is an open source package made open source by IBM Research, and among other things, it contains a few dataset classes. For this problem, we are going to use the MEPS dataset, which helps us load and pre-process this MEPS data for this use case. So as with any problem, before even diving into modeling the problem, let's take a look at the data. So as you can see on your right hand side, you see some of the traces from the example notebook as linked into the slide. And you can see this is the tabular data format where typical attributes for the patients include gender and race. It includes even marital status and things like activity level and so on. So let's go through the modeling and the data steps. The first step, as with any problem, has got to do with data processing and cleansing. We are not going to go over those details in this tutorial. I encourage the listeners to follow the link on the notebook and work out the steps for themselves from this notebook that's linked above. Instead, we are going to look at the use case more from a point of explainability. So as mentioned before, we are going to use a directly interpretable model. Our model of choice is linear rule regression. Linear rule regression is a linear model that uses rule-based features. What it means is that these features can be conjunction and disjunction of various kind of rules, things that can often look like branches of a decision trees. It uses the recent advancements in optimization techniques to build such a model. For this problem, we are going to use rules as well as unbinarized ordinal features. Some of the tunable parameters include include parameters that can help the users to control the number of rules and the complexity of rules. That is the number of features in each such rule. These are inherently tied to end user explainability. For example, more complex rules can give better performance, but it may not be as interpretable to the end users than very simple rules that can often mimic clinical guidelines. So let's go through some of the modeling traces and the explanatory traces. So as mentioned before, we are going to use the AIX 360 package. The linear rule regression is a pre-built method that comes pre-packaged with the open source tool. It follows a largely scikit-learn compatible API. For this problem, we are comparing it with respect to the standard gradient boosted regressor that comes pre-packaged with scikit-learn. We followed the standard traces for the training and the testing. And as you can see, the test R squared for GBRT is slightly better than the linear rule regression method. However, the linear rule regression method are more directly interpretable. they generate features as mentioned which mimics largely branches of decision trees that are more interpretable to the end users, which in our use cases could be policymakers looking at such health expenditure data. So let's take a look at such features. You can see that the feature explanations can be called by just a simple uh, dot explain method. At the core, these models are linear models, and thus the coefficients can be sorted based on their absolute values, which in turn would indicate more important features to less important features in order of those absolute coefficients. A user can choose to see more or less coefficients depending on how many features they want to see. Coming to the features itself, they are actually rules as you can see on your screen. Some rules can be simplistic like the age rule, or some rules can be more complex such as rule 6, which has conjunctions over 3 or more predicates. These rules in itself can be largely useful to the end user. For example, rule 4 looks at the health status and the pregnancy status of patients, whereas rule 9 looks at the cancer. While these are useful by itself, to gain a better understanding, we can even look at deeper visualization. So let's take a look at the visualization about the GAM part of the linear rule regression model. So we can start by calling the simple dot visualize function call, and as you can see here, we are looking at the self-reported health status. This variable takes 5 values corresponding from excellent to very good to poor. The algorithm has given non-zero coefficients only to very good and fair. Even though this one might think that individuals in excellent health conditions should see a reduction in cost, or at least as great as those in the very good health status, uh, on the other hand, you can see that these are not that intuitive. You may expect certain different patterns. It is to be kept in mind that these statuses are self-reported, such so that like these values may not reflect the ground truth all the time. The absence of non-zero coefficients for poor health status may indicate some problem. For example, it could be explained by the low frequency of that kind of feature in the data. We can even look at some other variables. So for example, if we look at the smoking status, this is again is a very counterintuitive example. A value of 2 here indicates that the individual does not currently smoke. However, the model has assigned a positive contribution to predicted costs for this particular feature. So it kind of indicates that there could be some confounding in the data. For example, for this problem, the average age of smokers was 44, whereas the average age of non-smokers is 49. Thus, the higher percentage um, can be explained by the following, that older individuals are generally more costlier population from a healthcare expenditure point of view. Thus, these two examples kind of illustrate that even if our performance of the models are good enough, we still need to look at and identify the important features and try to correlate that with our domain knowledge and intuitions to figure out that whether we have learned the right things, whether we have captured all the data, and even it can indicate us whether we have to handle certain kind of confounders in some special ways. So to wrap up this use case, I just want to highlight a couple of things. So in this model, we could even look at higher order rules. So rules with higher degree of conjunctions and disjunctions, which could potentially improve the performance, but may come at the cost of lower level of interpretability to the end users. We could also use this tutorial to figure out the high cost patient population, which again can be useful for the end use case. However, we are not going to go into those details. You can follow this link which is presented in the slide to look at the full tutorial from AIX 360. The takeaways that I want to end with this use case is that it is possible to build directly interpretable models for healthcare use case data. However, the decision is case by case basis, and we are going to stress upon some of them immediately after this. And also, which is going to be a huge theme for our tutorial, we are going to focus on open source tools that our audience can themselves use off the shelf and play with. So with that, I'm going to turn over to Kush to walk us through the next steps in this tutorial.
Now that we've gotten a good introduction from Daby and Kenney and a great example use case from Prithwish on the medical expenditure panel survey data, let's move on and take another view and look at the general dimensions of explainability. Explainability can be categorized according to four dichotomies. The first is, are we trying to explain data or are we trying to explain the model? The second is, are we aiming for a directly interpretable model, something that's simple and easy to understand by itself, like a decision tree or a Boolean rule set, or are we going for a post hoc explanation, which is built on top of a black box model, which is difficult to explain? Third is a dichotomy between local and global explanations. A local explanation is at the individual sample level, and a global explanation is an explanation for the entire model. And finally, we have static versus interactive. So a static explanation is just printed out and presented to the user, whereas an interactive one lets the user go back and forth with the machine in some sort of visual or conversational manner. Building upon the four dimensions or four dichotomies on the previous slide, here's an example taxonomy from the AI Explainability 360 open source toolkit for methods of explaining. And this would be used when you come to a new problem and you don't know what to do. You don't know what sort of explanation method is appropriate for you or for the personas that are going to be consuming those explanations. So you first off starting by asking the question, am I aiming for a static or an interactive explanation? And the question marks here just represent things that are not yet implemented in AIX 360. And the leaf nodes represent algorithms that are in the current release of AI Explainability 360. Right, so static versus interactive. So let's say we go down the static path. And now the question is, are we aiming to understand data or models? If we go with data, then there's different choices that we might have. How the representation will be for the data understanding. Is it based on features, in which case we might want to go with DIP-VAE, which can yield us disentangled representations. If we want to go with a sample-based approach, we can go with Proto-Dash, which provides a way to do case-based reasoning. And then if we are trying to explain models instead of data, then the next question is, are we aiming for a local explanation for individual samples or a global explanation for the entire model? If we can go down the local path, then the next question is, are we going for a post hoc method or a self-explaining method? So on the self-explaining branch, we have TED, which is teaching explanations for decision making, as one option. On the post hoc branch, again, we have the same question. Are we looking to explain in terms of samples or features? On the sample side, we have Proto-Dash again. On the feature side, we have choices among the contrastive explanations method, as well as more well-known algorithms such as LIME or SHAP. Now, if we go back up and are aiming for a global explanation for the entire model, then the question again is, do we want something post hoc or do we want a directly interpretable model? So a directly interpretable model would be a Boolean rule set, for example, which the Boolean rule sets with column generation or the generalized linear rule models can yield for us. And on the post hoc side, we might want a surrogate model such as ProfWeight. These are just examples. There's many different explainability methods out there. This just represents a subset. Now let's delve a little bit more into the details, asking the question on data versus models. So when we are trying to understand data, it's important to use a case-based reasoning sort of approach based on other samples and examples, so similar other examples, prototypes, and so forth, as well as criticisms, which help us kind of place a given sample with respect to what else is going on. At the feature level, the case is different. So we actually want to have features that we can understand. And if we're given ones that we aren't able to understand, can we perform some transformation to help us yield features that are more explainable and understandable? We can also be looking to understand the distributions of a given data set. If we're going for the model side, really our objective as the user, as the consumer of the explanation, is to get an understanding of how it is that the model makes its decisions. So different personas and tasks might require one or both of these different dimensions. Some of the oldest approaches in machine learning and artificial intelligence were directly interpretable models, things like decision trees and so forth. Recently, there's been a revisiting of directly interpretable models because most of the older methods were learned in a heuristic or greedy manner, but advances in discrete optimization have led us to look at new ways, new optimization approaches for learning large-scale directly interpretable models. And there can also be the case where we're dealing with models that are not directly interpretable. So things like deep neural networks or very large ensembles are not understandable to us. So we need to do a post hoc sort of explanation on top of them. And there's various methods for doing so. A local explanation is for a single prediction, whereas a global explanation describes the behavior of the entire model. So as an example of who would want a global explanation, a medical professional society might want to know the overall behavior of the model in order to inform best practices for their membership. So this can be both post hoc or directly interpretable. Global explanations are possibly both, right? And local explanations are in the case where a patient may want to know why the model says specifically, just for herself, why she has cancer, why it's predicting that. So there's methods for that. Finally, on the question of static versus interactive explanations, most of the existing technology and way of doing things has limited us to static explanations, just based on the systems that we have. But interactive explanations offer us a whole slew of new ways to think about explanation. And as people, we usually explain in an interactive fashion to each other. We ask each other's questions. We want to dive into details and so forth. So we can think of interactive explanations as a sort of conversation or some sort of visual analytics. So now that we've talked about the different dimensions in the taxonomy, let's talk about how it is that we actually implement these ideas in practice. So it turns out, as most of you already know, the best machine learning tools in general these days are open source. And it's actually no different for interpretable and explainable machine learning. There's lots of different open source packages out there, and one of the biggest differences among the different options is their breadth. So here's a table of various open source toolkits for explainability. Almost all of them have local post hoc explanation methods like LIME or SHAP, and many of them have global post hoc explanation methods, things like distillation methods or proto-dash, which we talked about before. There's less that have directly interpretable approaches, and even fewer that have explanations for data that have self-explaining methods or explainability metrics, which are proxies for how a human might judge an explanation to be. And here are the links to all of those open source toolkits. So I'm flashing it on the screen so that you can see the links, and then later on you can go explore. and click on these URLs. So explainability is focused on data and models. So that's kind of a narrow part of the overall life cycle of creating machine learning and AI pipelines. So models are embedded within these larger structures, and model explainability is not enough to give us an overall picture of the accountability and transparency of what's going on. So a solution to that is a set of ideas, including data sheets, model cards, and fact sheets. And these are ways of documenting what's going on from end to end throughout the process of creating a machine learning system and reporting those as a means of providing transparency. So these can include test results, but also intended uses and so forth. As Kenney explained earlier, we want there to be trust in AI services that we use in the healthcare domain. The first way of doing so is applying general sort of safety and reliability engineering methodologies. The second is identifying and addressing new AI-specific issues and challenges, including the explainability and interpretability of models that we've been talking about. But there's a third thing that we can do, and that's creating standardized tests and transparent reporting mechanisms on how services operate and perform. And this is not a new idea. For lots of safety critical systems, there have been fact sheets that get produced. So this is an example of a window sticker from a car that you might be looking into buying at the dealership. So there's a lot of different test results reported. So fuel economy in different operating conditions, whether it passed various sort of safety checks, what sort of features it contains, and so forth. And we see the same thing now with fact sheets for AI services. So here's an example of an AI fact sheet for an audio classifier. So maybe the doctor's physician is dictating something that will then be typed in as notes, but automatically rather than having a person do it. Right, so this audio classifier would take in an input audio clip. It has a particular intended use, which is audio processing and so forth. So there's a lot of different information on an example fact sheet, and it includes a lot of different performance metrics, discussions of bias, robustness, and so forth, as well as information about the data that was involved in creating it. And this is just a snapshot summary view. So there's a longer fact sheet that you could look into in more detail if you go to the link at the bottom. So a fact sheet isn't just a piece of paper that you just have at the end. It's actually a methodology for governing the AI lifecycle better than you would without. So as we see, there's different personas that touch data and models as they pass along the development process. So there's a business owner who is defining the problem, specifying it in conjunction with the data scientist, who's then developing the model. There's later a software developer, there's a validator, there's continuous monitoring, and so forth. And as the whole process progresses or unfolds, we see that these facts get created and captured throughout the process, and they can be rendered at any time using various means. So this fact sheet process is actually not only a transparent reporting mechanism, but a mechanism for governing these things. So I've kind of given you a sense of explainability and the different dimensions it entails, as well as how we think about transparency through the model cards, data sheets, or AI fact sheets approach. So let me pass it back to Prithwish to continue from here. Thanks.
Thanks, Kush, for the great introduction to explainability and its different facets. At this moment, I'm going to take a little bit of circuitous route in this tutorial. We are going to invert the problem and discuss some of the critiques with explainability. This would in turn help us situate a tutorial which, as you know, is human-centric explainability. So to do that, let's start by defining explainable AI. So till now, we have looked at the various taxonomies for our explainable model. We have looked at open source tools that are currently available and are being built every day, improved upon every day. And we have even looked at a particular healthcare use case using one of such tools. However, when it comes to the definition of explainability, the problem is not well defined. Michael Hind, the paper which is referenced on the slide, argued that explainability at itself is a communication problem. As you can see on the slide, he defined an explanation as the process of communication from person A to B, whereas the person A makes justifications for their action or decision. Sufficient justifications usually lead to an increased trust of A's decision-making ability to B. The justification is usually made informally and often iterative, with frequent checks by both participants. So this definition is very interesting and kind of follows with the remaining points. Thus, you can imagine that explainability is really hard to define because A, there is no formal definition and in an even human-to-human setting, and B, when one goes from that setting to a system-to-human explanation, it becomes a really challenging problem, a problem which we don't have complete definition. Thus, you can think of explainability as an interdisciplinary problem where AI modelers needs to work with several other stakeholders such as domain experts as well as social scientists as well as ethical experts. At this moment, we also want to recognize the many concerns that have been focused by many researchers. Some researchers have claimed that explainable AI is not feasible. For example, humans themselves are not always able to provide accurate explanations of their actions. One might think of humans in certain situations as one-shot or few-shot learners and often an intuition engine. Also, there is the following argument that if an AI is sufficiently accurate, then there should not be any need for explanations. While these are very valid points and concerns, as we will see in the following sections, for very high-stake decisions like healthcare, explainability is still very useful and very relevant. Before going into some other aspects, let's look at some of the common methods and let's do a little bit of high-level critique of such methods. So as were mentioning, several methods of explanatory problems have been postulated in literature. And as with any freelance theorem, no method captures all aspects. And again, the problem is very ill defined from a modeling point of view. So it is not surprising that every method comes with their own known problems, own limiting use cases. We are going to focus on some common methods, which are explainer models and attention models in this slide. So explainer models are essentially augmented models that are itself very simple things such as linear regression or decision trees that are built to explain, or rather to train on the outputs of more black box model, and their feature importances are thought of as explaining the black box models itself. Cynthia Rudin, in her seminal paper, showed and argued that such explainer models are not too accurate. They don't follow the actual black box model so much, and thus limiting the acceptance of such methods for very high-stake decisions. Attention-based models are again a hugely popular class of models. In this type of models, people usually get a notion about which features the models were looking at in terms of making their predictions. However, they don't get a rank list of feature importances, which could be useful in some scenario. Even with the limitations, attention models have other problems. Recent research have found that attention maps may not be unique, and even one can get very different attention maps for the same kind of model. Also, they have been found to be easily tampered with using adversarial attacks, and which is not really surprising because when a model is, or when the inner mechanisms of models are usually known, uh, like how to devise adversarial attack is possibly not completely out of the realm. So given all of these challenges, there is this alternate viewpoint as should we directly build simpler models? And Michael Hind, in his seminal paper, argues, and which we were also referring to back minutes earlier, that higher the impact, more likely is that we need explanations. So Cynthia Rudin argues in her seminal work that there are simpler models for most high-stakes problem, and it is possible to find them. Her argument is actually against this oft shown graph on the right, which shows that explanation usually comes at a cost of performance. The x-axis of the graph is explanation effectiveness, and the y-axis is the learning performance. This graph was adapted from the DARPA XAI challenge, and it mentions that the green dots are essentially the farther away you go away in the explanation landscape, the lesser performance you typically have. In her paper, Cynthia Rudin actually showed that for a certain class of problems, it is not always the scenario, and it is possible to find these simpler models. She provided a nice theoretical framework using Rashomon curves, which under certain scenarios can prove or disprove the existence of simpler models in certain use cases. However, she also identifies domain expertise and optimization difficulties as some of the key challenges in order to develop completely self-interpretable models. So with this landscape in discussion, we now come to this argument that even when you have self-interpretable models, and forget about black box model itself, they may not be always satisfying all the requirements for the end users. As mentioned before, explainability at its heart is a communication problem between person A to person B. And who this communication happens with largely can define what are the requirements for explainability. Michael Hind, and to paraphrase him, quoted in this paper, explanations for whom. In his paper, he mentioned 4 groups of people, starting from the AI system builders, going through the end user decision makers, the government decision makers, and end users. Each persona has the specific requirement for explanations and are motivated by different aspects of the problem. Whereas the AI system builders usually require explanations to monitor the system performance and for debugging purposes, the end users, who for an example like a healthcare scenario could be the patients, desire explanations that can help them understand their own experiences with the model. Thus, whereas AI system builders usually require low-level interpretability of models, users, or in this case like the end users like the patients, would likely need to have reasons for their specific outcomes as predicted by models in a very simple manner. On the other hand, end user decision makers can require explanations for building trust, whereas government decision makers may want explanations to make sure that decisions are made in a safe and fair manner. With this background and landscape, we can thus focus towards the main tenet of this tutorial, that is human-centered explainability. Following Michael Hind's guideline, we then need to identify the healthcare personas and their requirements in order to build such explanatory models. Just to recap, as in a general setting, explainable AI could be thought of the following players. You can think of each of them interconnecting with each other to share their experiences, share their preferences, which can, for example, the preferences from end users can um, can define how the AI system builders are building their own model. When we focus on the healthcare persona, we can then define or rather bucket the personas into these three scenarios. We are not covering the patient persona as that is a very different use case which is outside the scope of this tutorial. For now, we can look at the data scientists, the clinical researchers, and the clinicians. Whereas the data scientists, for example, are well versed with AI and ML and stats and are typically more concerned with model performance and model level explanations, a clinical researcher often tries to tie back such model performance and model inference with their clinical background, tries to correlate that to the vast body of literature in medical informatics. While they can speak AI and ML, but they are more in an applied setting. Thus, their main explainability requirements can be thought of as instance level. That is, they want to make sure certain specific prototypical examples in their mind are explained by the model in a correct manner so that they can increase their trust in such models. They could also be involved with KPI or key performance indicator analysis for such models to actually recommend the use of such models in clinical practice. And finally, and perhaps the most important persona for healthcare, the clinicians, they have a vast body of domain knowledge and they are usually only concerned with the patient-centric focus and want the models to be applicable to their patients and then to provide sufficient instance level explanation for the patients for them to use such models. We want to stress up the fact that these roles can be translational. Uh, these roles could also be played by a single person or multiple personas. So, for example, the same person can act as a clinical researcher or a data scientist in different setting. We mainly bucketize these personas based on very coarse criteria, and we would assume a person wears one of their metaphorical hats, such as data scientist while doing one analysis and their other hat while doing some other analysis. So we have defined these healthcare personas. Going into the remaining part of the tutorial, let us dig a little bit deeper into some of the deeper value of explanations. So why do we require explanations? As mentioned before, explanations can be typically thought as a communication problem from person A to person B. So in a healthcare setting, you can think of, for example, between clinician and patient, these are requirements that can help them inform current and future decisions. We can think of that as a distributed cognition between a human and computational agents. And if we look into the theory of mental models, we can then think of explanations helping the clinicians or, for example, patients build their respective mental models. If we just focus on the clinicians for a time being, we can think of the clinicians looking at several aspects such as their medical knowledge, the model predictions, the model explanations, and the patient history to help build their mental model for the patients, their disease state, and what they can take into in order to best serve the patient. And explanations can thus are a requirement that help the clinicians build the bridges and complete the mental models. Thus, going back to our theory, this can be thought as a distributed cognition framework, and usually this can be iterative, where in an ideal setting, the explanatory display or the explanatory model should be able to provide enough information to the end users for them to help build this at the final time. So one can think of from a clinical use case as explanations being different requirement based on the type of study that is being done. We are not going to go through all of these. The slides will be available on the website, but focusing on a couple of them, for example, counterfactual, these kind of studies then has to deal with what if scenarios and can help an end clinician or user determine whether certain kind of settings are useful to them. It can go all the way back to more rigorous statistical models with more statistical guarantees and so on. We finally want to conclude this section by taking a quick look at what such a questionnaire for explainability could look like for a end clinical use case. You can see that these covers various things such as what are the inputs, what are the outputs, how does the model produce this output, why does the module produce this output and why not, and certain other things. And with this, you can start to see that these have certain similarities with model cards and fact sheets as presented before by Kush. We want to stress upon that this work is currently undergoing, and the community is working largely on many different concepts that we think in future would help build such questionnaires and answer such questionnaires directly from systems. With this, we want to conclude this section, thus sufficiently motivating us about the need for human-centered explainability. I want to hand over the tutorial's next part to Sanjoy, who's going to walk us through some of the important models for explanations currently in practice. Thank you. Okay, thank you. So we are going over to our part 3, and we'll be going into the models itself. We will be taking a break at 12:30 as per the KDD guidelines. So please stay on with us till then.
Thanks, Prithwish. I'm Sanjoy Day. I'm a research staff member at IBM Research. In this section, I'll go through some of the most commonly used interpretable AI methods in details. So in this section, we'll describe a few generic interpretable AI models which have been used in multiple domains, including many healthcare problems. As mentioned by Kush earlier in the previous section, there exists a vast body of literature of interpretable AI methods. We are selecting a few representative ones from the taxonomy showed in the right panel. Some of the criteria for selecting such representative methods were the general state of the art, their ease of use, and their popularity in the healthcare domain, and also sampling the branches of the taxonomy shown here. Due to lack of time, we cannot cover each of the branches of the taxonomy. We refer to the tutorial webpage for further readings. The first method we choose to explain is LIME, or it's called Locally Interpretable Model Agnostic Explanation. This is a very popular method and very widely used, irrespective of domains and data types. Let me first show where it falls within the hierarchy of the taxonomy we are using here. So if we start from the top, it falls into the category of static model because it doesn't take any interactive inputs from the user. Next, in terms of the dichotomy between data versus model, it is a model-based approach because this model directly tries to provide explanation using their own optimization framework. The next important characteristics of the model is that it is a local model since it tries to provide explanation for each individual sample, although it tries to summarize those local explanations generated from different samples into the global level using some post-processing steps. Another important feature of LIME is that it is a post hoc model agnostic explanation method because it can take any complex model as its baseline and provide explanation out of it. In contrast to other explanation model which tries to modify the black box models itself to generate some simpler model and then interpret those model itself as an explanation. In terms of the final output of the model as explanation, it generates the most important features of a given problem, and those important features can be used as a best possible explanation of the baseline model. Let me first show an example about the output of LIME's explanation for a text classification problem. So here we're showing the results from two explanations generated by two algorithms, and the task is here to classify a text document whether it is related to Christianity or atheism. And here the words marked in red color basically denotes their association with atheism. And we can see here that algorithm 1 is much more explainable than algorithm 2. So this is the main contribution of the LIME method, is that once we provide this kind of explanation, it becomes easier to choose between different algorithms. Okay, so let's dig deeper into the algorithm itself. So let's first discuss about the main key assumptions of the model. So in this slide, I'm going to show the objective function of the LIME method in details. So let's first quickly look at the notations of the objective function here. So the f is the original complex function which LIME is trying to explain for a given sample x, and f is the simple interpretable model that LIME is trying to learn within the local neighborhood of the given sample x, and that is denoted here by pi x. The main objective function comprises of basically two terms. The first term determines the local faithfulness of the interpretable model within the local neighborhood of x, and the local faithfulness of the two functions f and g should be similar, at least within the local neighborhood of x, which is denoted here in the second equation. Now let's look at the second term. So the second term basically is trying to control the complexity of the explanation itself by imposing some regularization on the explanation model. Another point we want to emphasize here is that the input domains of these two functions f and g may be different based on the problem domain. As I mentioned earlier, by illustrating the examples of bag of word and the embedded features in the context of learning text classification. And these two input feature sets are represented here by x and x prime. So when you optimize this loss function, you learn the new explainable model G, which is much simpler than the original non-explainable model F. So this is how LIME works. Another cool features of LIME is that it can also generate kind of a global summary explanations from the local explanation that it had already generated from the given samples. Let's look at the bottom right figure for illustrating this SP-LIME algorithm. So here each row represents a sample that is being explained, and the columns are the features which is the most representative one for explaining that particular sample. What SP-LIME tries to do is to pick those samples and features that can cover most of the cells in this matrix in a non-redundant fashion. As an example, if we pick F2 as the most important explanative features, it can cover 4 out of the 5 samples here. And similarly, if we pick the second and the last samples, it also can cover most of the features of the matrix. So this is how the SPLime works, and it basically kind of a heuristic algorithm to generate the global summary explanations from all the local explanations. Another widely used explainable AI method is called SHAP, or Shapley Additive Explanations. This is very common in many applications, including healthcare domains, and this is because it has a very strong theoretical guarantees, and it is similar to Lime in terms of where it falls in the taxonomy that we are using here. So it's again a static method, and it's a model, and it is also a kind of a generic version of many different local explainable models, and it's post hoc, and also it basically creates feature importance in terms of how to define explanation of a particular model. So the main contribution of the SHAP method is that it can provide a generic framework for many local post-hoc explanation methods. And more importantly, it provides a nice theoretical framework to prove the unique existence of such local models with certain assumptions. And another nice feature about this shape method is that it can provide the shape values for each of the features in terms of how they're related to the task being learned, and those shape values can be used for determining the feature importance. And finally, this framework provides different techniques to compute this kind of shape values very efficiently, especially in the presence of multi-collinearity among the features. So now let me define the basic ideas of this framework, and how this framework generalizes most of the local methods. So here again, similar as Lime, x and x prime represents the two input dimensions. One is for learning the original predictive model, and the other one is for the explainable model. So given that original function f and a local sample x prime, the goal of any local method, it can be generalized here, is to learn a new function g as z prime. Here z prime is kind of a local neighborhood of x prime. All it's trying to make sure is that the two functions are similar in the local neighborhood of x prime. So SHAP basically is generalizing it into a additive feature attribution method, which is kind of a linear weighted summation of all the feature components zi, where m is the dimension of this feature domain z. And also here the phi's represents basically the feature importance. So using this generic framework, they try to show that many existing local explanation models can easily be casted into this framework. Examples include Lime deep lift, layer-wise relevance propagation, and the classic Shapley value estimation. So once all the local linear explainable models can be casted in this kind of generic framework, as a next step, they wanted to show what are the basic properties of this of these local linear models that it should satisfy to have a unique solution. So as a first step, they try to define those shapely regression value phi I, which can be intuitively interpreted as a surrogate for feature importance. So now in this equation phi I, it basically is trying to determine the difference between the function scores when you include these features with any subset of the given features. So now this shape framework basically described three different properties that any additive feature attribution method should hold, and the first property is the local accuracy, which is similar to the definition of local faithfulness of Lime. So basically all it is trying to say is that given a local sample X, the model F behave similarly for the simplified input X, at least within the local neighborhood of the original sample X. And the second property is missingness. So all it says, if the transformed simplified feature space, the X prime is 0, then the shapely regression value phi should be also 0. And the third property is consistency. So by consistency, it means that if the contribution of a particular feature stays same regardless of other inputs when you change the model parameters, then the inputs attribution phi I should not also decrease. So this is kind of a non-increasingness property of the feature attribution function. So based on these three properties, they provided a theoretical solution using game theory to guarantee that a unique local linear explanation model is always available when all of these three properties are satisfied. So one problem with this shapely regression value is that it is computationally expensive. So this shape framework also provides some approximate algorithms to find these shape values efficiently. Basically, they provided 4 different algorithms, namely shapely sampling values, kernel shape, max shape, and deep shape. Intuitively, these approximate algorithms can be shown in the bottom right figure. So here in the x-axis, it is trying to represent the phi I values based on how much the predictive performance increases when you include that particular feature successively into the model framework. So basically the idea is here, if the changes in terms of expected predictive performance increases or the changes are following like a similar dimension, then the shapely values is higher versus when it get reversed, then the shapely value is not good and basically have some multi-collinearity present at that moment. So based on all this approximate algorithm, it provides a nice framework where you can compute shapely values for all different features that are available for a particular task, and you can interpret those shape values as kind of a feature importance of the task being learned. So as a next representative model, where we choose contrastive explanation. This is kind of a newer method than the previous two that I just described, and it has been successfully used in many different domains. The nice feature about the contrastive explanation method is that it can provide more natural explanation, not only in terms of kind of providing explanation about the positive features, but also the negative features which should not be learned for a particular task. In terms of where it sits on the taxonomy hierarchy that we are using throughout this tutorial, it is actually a static model, and again it's a local model and also post hoc generative model, and it also provides features. So it is similar to Lyman shape in terms of their position in the hierarchy of the taxonomy. So in this figure, we are describing the contrastive explanation method, CEM, in details. So there are two terms that is very critical to understand this method. So one is called pertinent positives, and then the other one is pertinent negatives. So pertinent positives means the features that should be minimally and sufficiently present for a particular task to predict from the same class. And the pertinent negative means just the opposite. So it defines the features that should be minimally and necessarily absent for that particular classifier, so that it should not predict the opposite class. So let me give an example, then it will be easier. So let's say in healthcare domain, a patient is showing some symptoms of cough, cold, and fever, but no sputum and chills. So the question is now how to differentiate this patient between these two possible uh, uh, disease like flu and pneumonia. So cough, cold, and fever, those are common between these two diseases like flu and pneumonia. However, the absence of sputum and chills are a diagnostic feature of flu. So basically, to define flu with with fair amount of confidence, we need the patient to have fever, cough, and cold, but also we need to make sure that they don't have sputum and chills, just to differentiate those patients from pneumonia. So in this case, the pertinent positives will be cough, cold, and fever, and the pertinent negatives will be the sputum and chills, and both are important to diagnose a patient accurately and to differentiate it from like other similar diseases. So the paper actually also gave a very nice example. This is from the original, the means dataset for classifying digits. So each column is for, like an output of a particular algorithm. And let's look at the first row, which is for classifying digit 3. So the cyan part, which is the second column, CEMPP, pertinent positives. So the cyan features highlights the most important pertinent positive features for 3, versus the column 3, which is in red, shows the pertinent negative features. So you can rightly see, like, this red part of the features is very important to distinguish 3 from 5. So if we don't have pertinent negative, like as in the second column, only with the cyan features, then yes, of course, it can classify 3, but it cannot contrast with like other possible digits like 5. So this is the main contribution of this CEM method, which not only shows the positive pertinent features, but it also shows the positive, pertinent negative features, which is important so that the sample is not classified to the other classes. And this is the main contribution in contrast to NLP or Lime or SHAP, because they only highlights the most important positive pertinent features for a particular digit, but not the pertinent negatives. So let's dig deeper into this CEM method, and I'll describe here how the algorithm can find the pertinent negatives and pertinent positives. So first, I'm describing here the pertinent negatives. And the basic idea about finding the pertinent negative is that given a data sample X naught and its target class level T naught, all it's trying to find is the missing components of the same class T naught. So let me now define the loss function here. The loss function comprises of three components. The first one is the one which wants to make sure that the perturbed sample belongs to any other class than the given class T naught. So basically the idea is that once you perturb the given sample X naught, it tries to make sure it switches the classes T naught to the other possible classes. It further includes a confidence parameter K, and that tries to provides an additional separation between the two predicted classes of X naught and the perturbed sample X naught plus delta. The next term in the loss function is the regularization terms, and this is like an elastic net regularization types of framework where both L1 and L2 norms are used, and this is particularly useful for large scale data. And the last part of the loss function is the autoencoder reconstruction loss. So this part wants to make sure that the original given sample X naught and the perturbed sample X naught delta are similar when they are assessed by the L2 reconstruction error of the autoencoder. So similar kind of loss function can be defined for finding pertinent positives as well, but the only difference is that the perturbation is defined like an union from the same classes of the samples, right? So this is the delta, which is X union X naught, and then they want to make sure basically that the modified sample, the perturbed sample X naught, will have the same top one class prediction from the same class that of the original sample. So basically the only difference in the first part of the loss function from the previous one, and here we can see that it wants to maximize the prediction of the perturbation delta from from the same classes of other samples basically. And again, there is a perturbation difference parameter K, which is an hyperparameter to optimize. So let's discuss a healthcare use case based on the CEM algorithm. The problem is here to differentiate between autistic and neurotypical subjects. The features used in these problems are fMRI images of brains. The raw imaging features were summarized into 7 topmost brain regions, which is shown on the third and the fourth figures. So each row represents a region of interest, and the columns represents a subject which has to be classified between either autistic or neurotypical. Now the two heat maps are showing here the results of CEM algorithm, and the right one is for LRP algorithm. As we can see here, CEM algorithm highlights two different coefficients, one for pertinent positive and another for pertinent negatives. However, in the last figure, LRP only highlights feature importance by a single entry in the heat map. So this actually shows the effectiveness of the CEM algorithm, which can identify both pertinent positives and also pertinent negatives for each of these subjects. And it turned out that the results are consistent between these two algorithms. For example, two regions of brain, namely DMN and visualization, are mostly related to autism. However, C method provides more details about how these two features are related to autism in terms of whether they're pertinent positives or pertinent negatives.
Okay, so that brings us to the scheduled break. We are 5 minutes over. So thank you for keeping tuned. So we will be pausing the screen share at this moment and we will come back in 30 minutes from now. So we will be starting at 1:05 Eastern. Thank you. And yeah, hope to see you after the break. And in the meantime, feel free to use the chat. We will be monitoring that as well. Thanks. Okay, so we are back. We are resuming our tutorial. There was a few questions. So Amit, I think there was a question on model agnostic explanation methods. I wonder if you want to pick up on that question. Otherwise, we can also do it at the end of the QA.
Sure, yeah, I can pick up on some of the questions. Yeah, hi, Srinivasan. Yeah, so I guess the first question from him was, is computational complexity a bottleneck for model agnostic methods like CEM and LIME? Firstly, CM is not model agnostic. So it directly sort of takes access to the neural network or any other differentiable model. However, we have a model agnostic version of it called model agnostic CEM. And So for that, yes. So the computational complexity of the MACEM version will be higher than Lime, and the reason is simply because so Lime, like as presented by Sanjoy, just highlights important features. So there's no question of like searching for a different point or so on and so forth. So in CEM, like you saw, you actually have to find a contrast point. So it's like a non-convex optimization where you have to search to find the point that lies in a different class than the original point. So it's kind of an incremental search procedure, which takes more time than say standard Lime, where you just essentially just sample, perturb your input, get a few samples, and then you just fit some linear model and see what features stand out. So in that sense, CEM is more time consuming, but it also provides more information. The second question is from Srinivasan again, is are model agnostic explanation methods more secure? Is there a possibility of direct explanation models leaking model parameter information? So yeah, I mean, better the explanation method or more fidel the explanation method is to your original black box. Of course, it's kind of a negation of privacy in that sense. So you will, of course, get more information about the model. In fact, there's some recent work that we have done, and we have a paper on archive which I can probably share the link. Although the next part of the tutorial will sort of give you a reference to that, where we show that just using contrastive explanations, we were able to build global models that were transparent and more consistent, locally consistent with your with your black box model than say just doing some other procedure where you just directly train on the original data or just the predictions of the black box model. So yeah, so if you have better explanations, or in the ideal case, if you have a globally interpretable model that fits very well to your original black box, then yeah, privacy could be compromised. Third question is, are there explanation methods which have causality element to them? So causality is a very strong thing. I mean, there are a lot of methods actually which are very popular now, right now, called also counterfactual methods. And frankly speaking, none of them are really counterfactual. They are all, in a sense, contrastive. And it was one of the reasons we actually decided to name the method not counterfactual explanation method, but contrastive, is because technically, if you look at what a counterfactual is from Julia Pearl's definition, it's something which is very, very specific and personalized. So though there are a lot of methods claiming to be sort of causal in some sense, I think you should take it with a pinch of salt. One of the reasons is that for a true causal method, you really have to know how the data was generated. It's not enough just to like perturb inputs and then say that this is causal, because there are a lot of interdependencies which jump in, where you can't just like change features in isolation because they can have sort of downstream effects. So all those things have to be taken into consideration. So I think most of these methods, like the CEM or even some of the counterfactual methods, you can consider them as some kind of sort of a guideline or some kind of a reference point to help you figure out what's happening. But I wouldn't go as far as saying that they are causal in that sense. There's also a last question on, in your opinion, what are the drawbacks of Lime, SHAP, and CEM? So yeah, in a way, so Lime and SHAP are kind of proxy methods. So there could be again an error in terms of what they are explaining and what's truly happening. Secondly, they don't give you contrastive information. For CEM, the drawback is, like I said, it's more computationally intensive, but it can give you sort of this contrastive information. And again, like Sanjay pointed out, so there are certain things in CEM, like if you have an autoencoder, you can make the explanations more realistic and so on and so forth. So all that can help making it more sort of tightly connected to your true data generation procedure. but again, that adds more complexity to the whole scheme. So I think so there's definitely a trade-off between the amount of insight you want and the amount of sort of resources you're ready to spend. So I think that's all I have to say about these questions. So back to you, Prithwish. Thanks.
Thanks, Amit. That was a great explanations. I think we are going to switch the recording, screen sharing. So just give us a minute. And in the meantime, yes. Okay. Yeah. So okay. So let's maybe Daby, if you want to start playing the next section after the break.
Now we're taking half an hour break and we'll reconvene at 10 o'clock. Thank you. So welcome back to our tutorial on explainable AI method for healthcare. Before the break, we talked about three different representative general explainable AI methods, namely LIME, SHAP, and CEM. So now I'm discussing the last representative method from this taxonomy. This is called Proto-Dash. This is kind of a little bit different than the earlier three models in terms of where it stands in the taxonomy. So it's a static model, but it relies on the data rather than generating explanation from the model itself. And it was also local and post hoc model, so it can basically take any complex model as its baseline. However, it is significantly different from the previous three methods like LIME, SHAP, and CEM in terms of the way it produces the output, which is the representative samples of from the data. So instead of generating features as an explanation, Proto-Dash basically tries to find the most representative samples or the outlier samples from a given dataset. So the main goal of the Proto-Dash algorithm is to find samples or examples that are the most representative one to summarize the underlying complex data distribution. And the way it generates this kind of representative samples is by assigning non-negative weights of importance to each of the samples. And it not only can find the most important prototypes for a given dataset, but also using the same non-negative weights, it can also find the outliers for the same dataset in a single framework. And one of the main contribution of this Prithwish algorithm is to define a scoring function which holds the submodular property, which I'm going to define in next few slides. And they also showed that based on some weak assumption of those submodular properties, they can design some efficient algorithms to find the best prototypes and also the outliers within a single framework. Another important contribution of this Prithwish framework is that it works for any symmetric positive definite matrix, and this is in contrast to the existing state-of-the-art method like L2C, which requires further conditions imposed on the kernel matrix. In contrast, Prithwish can generalize those kernels by using only symmetric positive definite kernels, of course with an expense of foregoing the submodularity. Let's now dig deeper on this Prithwish framework and try to see how it works. So formally it can be defined as an approach which is kind of finding a subset S out of a collection BV of items, which can be either data points and features, that maximizes a scoring function Fs. The whole framework is built upon one of the important property called submodularity of the scoring function Fs. So by submodularity we meant given like two sets S and V, and we want to find a data sample I which doesn't belong to T, which holds the following property. So by this property it says that the functional score, when we include this sample I to a subset S, it increases the score Fs more than when we add that sample I to the superset T. So whenever such condition is maintained, there are nice theoretical properties which guarantees that it can find sample prototypes very efficiently. However, it's computationally expensive to guarantee the submodular property of an algorithm. So instead, in this framework, the authors tried to relax this assumption of submodularity and defined a class of approximate submodular functions. And based on those approximate submodular functions, basically defined two efficient algorithm to search for this kind of prototypes. The first one is proto-greedy, which has less assumptions, but Prithwish is the first version with more assumptions. So in this slide, we are showing some examples for the means digit prediction classification problem using the prototypes. So the first panel shows the representative or prototypes for a particular digit, and the lower panel shows the criticism, or you can think as like an outlier for that particular digit. And the columns represent the two algorithms that we are showing here. So one is the Prithwish, and it contrasts with the L2C, which is another similar kind of prototype-based algorithm. And we can see here for the representative samples, they looks much more kind of closer to the original digits in terms of Prithwish than the L2C. And in terms of outliers also, the Prithwish can basically select like the most extreme outliers for the same digits. For example, like the zeros, Prithwish is definitely picking the outliers versus L2C, where the digits 0 and 7 almost looks like a true positive samples. In this slide, we are also showing another example of Prithwish. So this is applied on a CDC questionnaire data that is collected for census purpose, and the data contains a successive set of questionnaires sent out to a particular neighborhood. So the problem is here, can we rank the order of the questions based on some measure of importance? And for a given question, can we select the most representative other questions from this questionnaire data? So the way Prithwish handled this problem is by computing the top 10 prototypes for a particular question queue, and then it ranks all these questionnaire for this particular ith question based on this metric Rij, so that it can rank ultimately all the questionnaire based on the average rank matrix Rij. So in the right panel, it is showing the most important features or questions that are related to income. And it turned out that the topmost two features are early childhood and occupation. The occupation is intuitive to have to be related with income. The earliest childhood also has been reported to be a determinant of income as an indirect factor measuring a person's social economic status. So here in the next section, we are trying to describe some benchmarking techniques of these explainable AI methods. So the problem is here, we have explained a few different representative AI explainable methods, and there are ever increasing number of methods available in the literature. So the question comes, how to select the best explainable method, or how to benchmark the different explainable models for your particular task. So one of the few challenges, actually one of the main challenge for defining such benchmark for explainable model is that there is no different or no definitive metrics that is available for measuring the model explainability or interpretability, because most of the time it's very subjective. So this is unlike the commonly available metrics for performance evaluation of a predictive model. Because for supervised models, let's say you have many different metrics like accuracy, area under the curve, C index, for measuring the performance of the supervised model. And similarly, you have like other metrics like Chul coefficient, etc., for the unsupervised model. But for explainability, so far there is no well-defined metrics that can measure the explainability of a model. So it's very subjective so far. And most of the model therefore focused on the model complexity rather than defining the complexity of the explanation itself in terms of when they evaluate the explanation. So often they assume that the simpler model often leads to easier explanation between inputs and outputs. So there are two different ways of building interpretive model, as we described earlier. One is modifying the black box itself, and another is generating post-modeling explanation. And the metrics or standards differ for these two types of explanation. So we are going to explain that in next slide. So the explainable model, which basically modifies the black box models itself to make it interpretable, is kind of easier to benchmark, because then you can use the original metrics that are used for model performance, because it's just a modification of the loss function, right, the original one. So for example here, let's say you want to optimize a particular loss function of the original model. So to provide explanation, you can provide some additional regularization on the complexity of the loss function. And here we're showing a few examples of different representative black box model and how to extend those for this kind of additional complexities. And if we do that, and and if we treat explanation as like a sparse or regularized model,
then we can use the similar metric, the similar loss function, as kind of an evaluation criteria for those kind of explanation.
However, these kind of metrics are not readily available for any post hoc explainable AI models. So in the next two slides, we are showing two very generic algorithms which are capable of benchmarking any explainable model, uh, be it post hoc explainable model or modifying the black box model itself or any local or global models. So basically it takes any types of explainable AI models as an input and try to assess the quality of explanations. So the first method we are describing here is called ROAD, and it's a benchmarking framework using deep neural network. So the way it works is intuitively very simple. So it tries to drop the most explainable features generated by the explainable model, and then it retrains the model onto this newly generated data and try to see whether the accuracy performance drops because of removing that explainable feature. So the goodness of the explanation is basically defined by the drops in terms of prediction power when the model is retrained without that feature. So this is explained by the top right figure. So we are showing here the test accuracy when we remove the topmost explainable model in the x-axis. So you can see in the first figure the accuracy drops pretty dramatically when you remove the topmost interpretable features, as opposed to on the right side we are seeing that for a model the test accuracy doesn't drop when you remove the topmost interpretable features. So this framework also tried to analyze why this thing may happen, because it may be two possible cases when you remove the topmost interpretable feature but still the accuracy holds to be good enough. So what can be the possible explanation of these cases? So either it may be possible that interpretable feature is actually uninformative, or it may have some redundancy with some other features into the model. Therefore, although you remove the most explainable feature from the model, the other feature which has collinearity with this feature retains the prediction performance, and therefore the test accuracy doesn't drop dramatically as we expected. So based on these two criteria, or how much the accuracy drops, this ROAD framework can benchmark any explainable model and try to generate kind of a ranking or score to compare different explainable models. So here we are also showing a comparative study of a few different explainable models which are shown on the columns. These are base estimators, ensemble estimators, and control variants. So these are three different types of explainable algorithms. And on the rows, we're showing how much of the input variables are suppressed. And we can see here, no matter how much of the explainable features are replaced by random noise, the retention power in terms of text accuracy is pretty high still. The test accuracy here didn't drop enough to report those features as interpretable features. So this is how this ROAD framework can estimate or benchmark any given explainable model. So the next benchmarking method that we're describing is called fooling neural network interpretation via adversarial model manipulation. It is similar in flavor with the previous one that we described as ROAD framework. However, the way it works is slightly different. So the role framework didn't modify the baseline interpretable model itself. It only tried to tweak the dataset by replacing the most interpretable features that is generated by the model being compared. However, this adversarial model manipulation framework not only tweaks the data, but also it modifies the objective function to learn a new representation of the data. So what it intuitively is trying to do is to incorporate the interpretation results directly into the penalty term of an objective function, and then try to see how robust the interpretable models are when we manipulate the input data. Let us describe this problem by using this figure. So the problem is here to classify this big elephant from the bus. And in the second column, we are showing the results of the baseline model. So this paper is using two different baseline. One is LRP, another is GSAM. And the interpretable features produced by these two algorithms are marked by the color contour or the boundaries for LRP, and you can clearly see that the most important features marked by these two algorithms rightly points out to the elephant in the figure. Now, as a next step, this framework actually manipulates this figure by adversarial manipulation using several algorithms. Here we are showing the top four algorithms on the four columns here, namely location-based, top case, center mass, and active. And then the model is trying to basically learn this loss function where it is trying to see whether they can learn the new parameter W naught from the original parameter W given the new full dataset D full. So the idea is here in this new perturbed dataset D full, based on any of these four algorithms, it can mask off the most important features, and therefore if an algorithm, interpretable algorithm can be fooled easily. Based on the results here, we can see that for the location-based perturbation and adversarial manipulation, the GCAM is actually focused to such adversarial manipulation. However, the LRP method is fooled here because for the perturbation of the data, it still can differentiate elephant from the bus. So in this way, based on how much a model is robust to adversarial manipulation, any kind of explainable model can be benchmarked. This concludes our discussion on the benchmarking of AI interpretable models. In the next section, Amit is going to describe the knowledge transfer models.
Okay, so just give us a second while we queue up the next video. Are there any questions, feedbacks on this part?
Okay.
Okay, so let me share my screen again.
Thanks, Sanjoy. So now what we'll do is we'll look at a very important class of methods called knowledge transfer methods. And these have applications in interpretability as well as beyond, as we'll soon see. So the basic idea is this. Given that you have a black box model or a complex model, such as a deep neural network, that you know performs really well on your data, is there a way to transfer information from this complex, high-performing model to, say, a simple model of choice, say a decision tree or an SVM, that may be suitable for your application? So the simple model, a priori, just trained on the original data, may not have an acceptable performance. So this is essentially the problem that we want to address in this part of the talk. So, like I said, there are applications related to interpretability where a domain expert may have a preferred simple model that he or she understands, and he does not want to rely on local post hoc explanations, some of which you already saw. The other is in small data settings where you might have a complex or a black box model trained on a large public or private corpora, but then you get, say, small amount of data from a client or say from a hospital, and you can only build, say, a simple model on it given the size of the data. The question is, can you somehow leverage the black box model that you had already built to improve the simple model? A third setting is resource constraint setting. Say a model has to be deployed on your cell phone or say on a UAV where there are strict memory and power constraints. And so only a simple model can be deployed in such settings. And the question again is the same. How do we get the best out of this simple model? So the first type of methods that do such kind of knowledge transfer from a complex to a simple model try to essentially alter the target that the simple model fits to. So knowledge distillation is one of the most popular techniques to do that. And the idea is to essentially fit the simple model to soft predictions of the probabilities of the outputs of the complex model. And the soft predictions, the softness, so to speak, can be changed or altered by essentially tuning a temperature parameter that most of these complex neural networks have when you output. And the idea is then, rather than fitting the simple model to the original labels, you fit it to these soft predictions. So like you can see down here, like you have a neural network and then you get soft predictions and now you fit to these soft predictions. A specific case of this is model compression, where you actually try to fit to the hard labels. And this also has shown to improve simple models in some cases. The second class of methods, which are more recent, are sample reweighting based methods. So the idea here is, rather than changing the target, you actually keep the same target that's there in your original data, but you reweigh the samples. Or in reweighing the samples, what you would essentially do is you reweigh the loss of the simple model per instance. Simple models that don't allow reweighing, that don't train over weighted losses, you can essentially resample in that ratio and try to essentially do the same kind of thing in concept. So one of the popular methods for this is called ProfWeight, which transfers from a black box model such as a neural network to a simple model of choice. And the idea is this, is that many times neural networks are actually not good density estimators. So the output probabilities that you get are not really indicative of how confident they are in their prediction. So what you do is you attach linear classifiers, which are termed as probes, to intermediate layers of this neural network. And then for every training point, you try to get the probability of classifying that training point into the correct class. And there are obviously a few more details, but the idea is that when you take high enough performing probes, and the output also can be seen as probe 3 in this figure, or probe n if it's an n layer network, you basically take all these probe outputs, which are just essentially probabilities for classifying an input in the correct class, and you average them. And what you do is every input you weight by this average score that you get. And so what you see on the right is the general kind of behavior that you would observe, that if it's an easy example that's easy to classify, in this case a 7, you would see a profile like you see on the top right hand side, where at probe 1, it might be a little difficult for it to classify it correctly, but probe 2 onwards, it's much easier. And so the area under this curve, which is essentially approximated by taking averages of these probes, probe outputs, is basically an indication of how easy or hard that example is to classify. If you look at the right bottom, there's an example of an hard example where the 7 is not particularly well written. And what you would see there is potentially is that at lower level probes, it's very hard for the neural network to classify it correctly. But when you reach higher level probes of the output, essentially with neural network, you probably do well. But if you take, again, an AUC of this, you'd find that the AUC of this 7 would be lower than the 7 above, indicating that the lower 7 is much harder to classify correctly. And this would give you essentially a gradation of difficulty for examples. And now, once you have this gradation, you essentially use this to weigh the loss of your simple model and retrain the simple model. And this has been seen to give quite good results in some applications, which you can find more in the paper indicated below. This is another sample reweighting method, which is much more recent. And one of the ideas here is that rather than just taking the average, as I just mentioned for prof weight, you also take the simple model's a priori confidence estimate for that input, and you use that to divide the average. And that's your new weight rather than just the average. And and here too, I mean, there are more details in terms of you have to clip, since now you're dividing by a probability, you have to clip the weights and so on and so forth so that it doesn't go to infinity and other things. But the basic idea is you take an average, you take a ratio of the output, essentially average of the complex model divided by the probability of classifying that input to the correct class by the simple model. And you use that as a weight, and you essentially retrain your simple model. One of the things here is also it applies to not just transferring information from a neural network, but even for arbitrary models. Again, details are in the paper below. This is essentially a third kind of knowledge transfer to simple models. And what these methods do is basically take local explanations and create a globally interpretable model. So one could use SHAP-based explanations and do essentially do some kind of processing so that you can actually get global feature importances and so on and so forth. Similarly, you can do things with Lime, where you can not only learn local Lime models, but also group level Lime models and then a global Lime model. And this can give you essentially explanations, not just at the local and global, but even intermediate levels. A third method called GBFL, which is basically global Boolean formula learning method, can take local contrastive or counterfactual explanations and create globally transparent rules, which can then be used as a classifier by themselves. And all these three techniques essentially, in a way, transfer information from your complex model through local explanations to create something that's more globally understandable. Thank you.
Recently, various methods have been developed to visually explain and explore machine learning models, specifically for different end users, such as data scientists, machine learning engineers, and non-experts in machine learning and/or data science. They often prefer including visuals to start learning the model and using the model for their own problems. Here, we're trying to provide a quick intro to those methods. First, explainers. They provide web-based tools, often interactive, in which users can learn about how a model is trained from a dataset and how it makes inferences on new data points. They provide self-paced tutorials with scrollable walkthroughs and/or interactive playgrounds. Examples are R2D3 for decision tree model, GANLEV for generative adversarial networks, CNN Explorer for convolutional neural networks. Explainers are gaining traction, and we see more academic and non-academic venues that invite the work from others. Distill.pub and Viz Cross AI Workshop are the examples. You can search more examples related to various explainers in those two venues. The second category is visualization for model debugging and inspection. The methods are developed to understand machine learning models, to inspect any issues, and to gain insights on how to improve the model. Therefore, the visualizations provide interactive visuals tailored for such tasks. It often visualizes activations of neurons, aggregates them for layers, or visualize attention scores depending on the type of model architecture. Users can gain an overview and also query details on demand. The third type is data analysis tools. The tool is designed to support users' data analysis tasks in their own domains. In this case, users are often domain experts. The views provide information that are useful to answer questions that users have. In particular, users can conduct what-if scenarios by perturbing input data values and checking how decisions are impacted by the change. The tools also allow users to compare multiple model instances by showing differences in model outputs from same data input instances. Fourth category is a visualization method developed for specific explainability methods. The existence of user interface makes interpretable machine learning methods more useful. Chul is a great example for such a method. It provides easy-to-use toolkits where users can visualize the result of machine learning explainability in interactive computing environment like Jupyter Notebook. The four different categories shed some light on future directions. I believe there will be more tight integration between explainability methods and visualizations, and there will be more interactive visualizations where target users can interact with visualizations to understand the model better. Finally, there should be more tight collaborations between machine learning and visualization researchers and developers to provide user-centered, interactive explainability methods. There are plenty of visualization research areas where both fields can work together.
Okay, so before we go on to our next part, I just wanted to just mention. So all the recordings for these sessions are already in the vFairs app, and we will be, these are essentially also YouTube linked. So we will be linking them in our website. We will also be posting our slides in the website. Okay, so let's start with the next section.
In the following session, we're going to learn about what clinicians want from recent papers. We're going to take a look at a recent paper. The Pros et al. Conducted a survey where physicians were asked to report their understanding, explainability, and trust in 3 different machine learning outputs. First, machine learning with no explanation. Second, machine learning with explainable method, such as feature importance and ICE plot. Third, machine learning with model-agnostic explainability methods, such as Lime and Shapely. They provided visualizations and text description for those explanation methods in second and third. Here are the visualizations that were shown to participants with complementary explanation. Survey asks questions to estimate their understanding, perceived explainability of the method, and their trust in the model. The results show that there are correlations between understanding, explainability, and trust. For those who says they will follow the software recommendation after they are looking at the machine learning outputs, they are likely to be able to explain the decision to patients regardless of conditions. 88% of physicians preferred model-agnostic explainability methods. They also qualitatively analyzed free text comments about the explainability preferences. They seem to like easy-to-understand methods, visual, and positive, specific, patient-specific methods, preferably visual and graphic information about risk factors in the interview. What kinds of explanations do clinicians want? In a recent paper, researchers interviewed 10 clinicians. The results show following findings. First, researchers want justification for their clinical decision-making to patients, colleagues, or other stakeholders. They want the explanation to be aligned with current evidence-based medical practice. They also want to be aware of situations where the model falls short. Finally, they want to know the variables that are used to derive the decision. For reliable clinical machine learning, it is recommended to have well-designed explanation. There are 4 design goals for explanation methods. First, it needs to recalibrate clinician trust of model predictions. Second, it needs to provide a level of transparency that is necessary for users to validate model outputs with domain expertise. Third, it needs to reliably disseminate model prediction using task-specific representations. Fourth, it needs to provide actionable insights clinicians can undertake. Clinicians want feature importance to draw attention to specific patient characteristics of patients about how to proceed with them. Thus, they expect to see both patient-specific variable importance as well as population-level variable importance. Clinicians view instance-level explanations as finding similar patients. They want to use this in order to find effectiveness of actions taken for the similar patients. Thus, clinicians want to know the definition of similarity. These explanations are useful for research, but may not be useful in time-critical setting. Clinicians view uncertainty as a threshold for reporting results only when the model is very certain of its prediction. There are 2 types of uncertainties, modal uncertainty and data uncertainty. Temporal explanations can be useful to show patient trajectories that are influential in driving model predictions. For transparent design, clinicians want the model to reflect evidence-based medical decision-making method. So, model distillation can be useful to translate a model to a transparent design. How can we evaluate machine learning explanations? There could be 3 metrics. First, explanation needs to provide domain-appropriate representations. Second, it needs to inform actionable insights, such as follow-up clinical workflow, including rationalization of model prediction. Third, changes in model prediction need to reflect relevant clinical variability in explanations.
So that brings us to our case studies section. We'll start playing the video.
In the following slides, we're going to discuss a use case of data scientist for readmission prediction. This is work done by myself and collaborators at IBM Research. Machine learning is being applied to various clinical problems. Examples are drug discovery, medical imaging analysis, and disease progression modeling. This was in part due to more publicly accessible datasets, such as Mimic and UK Biobank. The trend is expected to continue for more tasks and data with more efficient algorithms. Clinical experts often see machine learning as black box. Because of that, there are many concerns about using the models for clinical practice and research. First, models can learn unreliable signals from data. Second, models can also amplify any existing biases in training data. Potential solutions are, first, we can use transparent models. Second, we can use model-agnostic methods to understand the attribution of input to output model decision. These methods are useful, but it is difficult for clinicians to use because they often do not have expertise in data science. In this case, interactive visualizations can be useful to inspect model, interpret model, and conduct what-if analysis. This can improve clinical experts' understanding and trust of the model. Therefore, we introduce our approach. We use interactive visualizations as well as Prithwish and contrastive explanations, so users can generate and interpret explanations for representative samples from population datasets. This use case, we train a model to predict unplanned readmission risks from clinical claims datasets. The dataset includes millions of patients with more than 500 features. RNN was used to learn the sequential and temporal patterns. Prithwish generates representative examples that best summarize the complex data distribution of the population dataset. For every model decision, contrastive explanation method also generates pertinent negatives and pertinent positives. Please take a look at details in the full papers in ICTM and URIPS to learn more about it. The visualization then shows explanations for selected patients. Top left view shows contrastive explanation. Each row has color bands which show how risk scores change as corresponding feature values change. In this view, users can select and move the lines to conduct what-if analysis for particular patients. Users can also show partial dependence plots for a single feature. Bottom view shows timeline of patients, where users can see details of temporal and sequential patterns of selected patients. Using this view, users can interactively explore the explanations about the selected patients generated from contrastive explanation modules and Prithwish. In future work, we plan to implement the technique as a full-fledged interactive visualization system and evaluate it. We also want to make CEM and Prithwish more interactive. We can also think of ways to give feedback to the model so that we can retrain the model for improving the accuracy. Thanks for listening. In this section, we looked at clinical researchers' perspectives. The particular use case is about disease progression pathways. This use case is from our recent paper called DPVis, Visual Analytics with Hidden Markov Models for Disease Progression Pathways. The paper is published in IEEE Transactions on Visualization and Computer Graphics. In this work, we collaborated with several clinical researchers and derived their research goals. Our researchers were interested in understanding disease progression trajectories from patient records. They want to learn how patients develop diseases over a certain observed period of time, which are collected as patient records or observational studies. They also want to find association between how they develop diseases and what characteristics they have. However, discovering and summarizing their trajectories is challenging when trajectories involve the evolution of multidimensional variables across time. Clinical researchers need to be in the loop for extracting and investigating disease progression trajectories. We used hidden Markov model to summarize states of patients' disease status as a function of their age and selected variables, thereby understanding their progressions with state sequence patterns. In this diagram, a patient has 4 different visits where multiple lab test results were collected. We select a set of variables to train the model with a parameter k, which is the number of states the model learns in an unsupervised manner. Hidden Markov models finds the most probable state based on the time or age with the values of the selected variables. Then, the model can assign the most probable state sequence by applying Viterbi algorithm on posterior distributions over states. The model can summarize patients' disease development using the sequence of states, and the state can be manifested by distribution of values over the selected variables. However, it is not easy to interpret hidden Markov models. Clinical researchers need visual aids to drive analysis using hidden Markov models. They want to interpret the states, distribution across variables. They want to gain a summary of state transition patterns for subjects. They also want to find association between measures and the trajectories. They also want to compare between subgroups in terms of trajectories, genetic profiles, and various characteristics of patients. DBViz is a visual analytics tool that is designed to fulfill the needs of visual support. The tool allows users to visually explore disease progression pathways, understand state characteristics, build cohorts, and visually compare the cohorts. I'm going to introduce the tool with a sample data set on type 1 diabetes. We explore observation data of 559 patients who are diagnosed with type 1 diabetes at the end. They were observed for various points of their age up to 20 years old. We modeled hidden Markov models using 3 variables, islet autoantibodies, with 11 state modeled. The goal is to explore the heterogeneous pathways before type 1 diabetes diagnosis with the evolution of IAs for patients. Let's start with static variable on top left. It shows patient characteristics with bar charts, and they are only observed once, such as biological sex, genetic characteristics, or country of their origin. Top right view shows current cohorts, where users can create, edit, and redefine cohorts for further analysis. State Query Builder allows users to query patients with a state sequence pattern. For example, users can query 0 to 3, which then will result in all subjects who follow the pattern starting from state 0 and ending with state 3. There are 2 main views of DBViz: clinical data matrix and pathway waterfall. Clinical data matrix explains states discovered by HMMs by showing distribution of data attribute values. This metric has rows, which indicate clinical features, and columns, which indicate the states. For example, this first cell can be interpreted as mean values of a variable called GAA for state 0, which is the probability of 0.02, which is very low. The cell is also color-coded with blue to red for low to high values for the clinical variables. We can also compare 2 different states based on overall distribution of data values across multiple clinical features. State 0 has blue cells, meaning it's a state with low values of the clinical features. Low values of those variables usually mean it's a state with less symptoms for type 1 diabetes. On the other hand, state 10 has more red cells, which indicate it's a state with high values, which indicative of more progressed state for type 1 diabetes. Pathway waterfalls show disease progression patterns for all subjects in cohort. The view shows colored dots and crossing lines. Each dot is a single visit of a subject. Color and vertical position both indicate the corresponding state. X-axis shows the age of subjects. Vertical lines indicate transitions between states. Here's a view shows patients' details. As you can see here, the numbered bubble indicates each subject's visits over its age. This particular subject shows patterns where they keep 0 states until the age of 140 months, which is 11 years and 8 months, then quickly progress into state 1, 2, and 3 at the end. Waterfall also shows the same pattern using the line. These 5 subjects who show the same state sequence pattern 0, 1, 2, 3, actually show heterogeneous patterns in terms of the speed of progressions. As waterfall shows, some progresses at age between 2 and 4, but others progress at an age older than 9 years old. Using this view, users can gain an understanding of multiple subjects' disease progression patterns in terms of the age states. By combining this view with clinical metrics, users can also interpret the progression with mean values of clinical features. Finally, there's a view for patient detail. It has density charts above. Red density and red symbol below shows the age of diagnosis for all subjects. Orange density and orange symbol show the age of diagnosis for selected cohort. We can see that the selected cohort, which follows 8, 9, 10 patterns, is diagnosed much later than the average diagnosis age. We can further expand density charts below, which also shows age of seroconversion in this case. Light purple for average for all, dark purple for cohort. Again, subjects in this cohort seroconvert much later than average for all. Overall, we found 3 trajectories using this dataset. We also discovered association between age of diagnosis and each of the trajectories. I will not go into details in this presentation. We reported some of the findings in the journal, so please take a look at to learn more details. Our team also presented in the clinical findings to ADA, which is a top diabetes conference last month. Here we show the benefit of visualization in our scenario. Clinical researchers need explanation, exploration, and interaction in order to use hidden Markov models for their clinical analytics goals. In DBViz, hidden Markov models outputs were explained using multiple coordinated visualizations. The interactive visualizations were used as media for clinical researchers to drive analysis. Clinical researchers can interpret disease progression patterns and derive clinically useful insights. This summarizes how visual aids in combination with hidden Markov models can help clinical researchers conduct explorative data analysis. In this section, we introduce a use case of clinicians. Here, we're going to discuss a use case of clinicians based on the paper RetainViz, Visual Analytics with Interpretable and Interactive Recurrent Neural Networks on Electronic Medical Records. It's also published in IEEE TVCG in 2018. EMR records patients' visits over timeline. We train models to predict a health outcome, such as admission, onset, or death, based on medical records like diagnosis, medication, and procedures over time. Medical records are sequences of those medical records, so it makes sense to use recurrent neural networks in order to take into account sequential patterns for computing outcome scores. However, clinicians want to know why and how model reached the conclusion. For instance, which visit was the most influential? Which diagnosis was the most influential? Will the outcome be different if the patient had received test A earlier? How can we do it for multiple patients? So, clinicians want to understand diagnostic risks predicted by the model. Clinicians want to do these tasks for multiple patients, so they also want to select patients with various conditions. For this use case, we used 5,962 patients' data with heart failure pulled from electronic medical records. We used the Korean Standard Classification of Disease 9th revision, which is equivalent to ICD-9 codes. We used modified attention-based RNN model called Retain. RetainViz supports similarity analysis. The first, projection view, shows dimensionality reduction techniques like t-SNE results. with scatterplot. Using this scatterplot, users can gain an overview. Users can also build patient cohorts together with other views showing distributions of demographic information and more. Users can switch axes and also select cohorts by using the lasso selection tools and take a look at the distribution for demographic information like biological sex, age, and risk prediction scores. Subsequently, we can add scores to generate contribution scores for each visit. Then we can create a heat map which can provide an overview of prediction and contributions of visits for a list of patients. Users can hover over different patients and compare their number of visits and also the risk prediction scores at the end and how each visit contributes to the risk prediction scores. Once the users find a particular patient interesting, users can select one patient by clicking on it. Then, users can take a look at treatment pathways for a single patient view. Contribution scores show how much each code, medical code, and visit affects the prediction score at the end. We use line charts above for prediction based on preceding visits at the moment and show each code's contribution score below. Users can explore how contributions change over patients' visits. Top K contribution scores can be also generated per patient. You can also generate it for multiple patients by aggregating the scores. Users can also conduct what-if analysis. They can do it by changing input values. The what-if questions can be answered by patient visit editor below. Users can add or remove medical records and update timestamps for each visit. The system then returns new prediction and contributions over patients' visits.
There is no sound for the segment here, so BC was just showing the visualizations here. I'll advance the slide to the next sound segment. Just give me a second.
Users can also conduct what-if analysis. They can do it by changing input values. The what-if questions can be answered by patient visit editor below. Users can add or remove medical records and update timestamps for each visit. The system then returns new prediction and contributions over patients' visits. So once users select multiple medical codes, they can also provide feedback so that the model can actually increase the attention scores for the selected medical codes and see if how that affects the decisions for selected patients. Users can also edit data values for a particular patient to conduct what-if analysis. As a result, the model view shows the red dotted lines, which indicates that the changes made by the users actually resulted in higher risk prediction scores across the timeline. Here are lessons learned from this analysis. Visual analytic methods like RetainVis improve interpretability of RNNs through visualizations. It also improves interactivity for experiments such as what-if analysis. We can also do mixed initiative model exploration and improvement methods using human plus AI through visualizations. It also implies future work on Viz plus AI method for health problems. We need to learn how to minimize false predictions. We also need to explain why sometimes model fails. Perhaps we can explain with examples. The system also needs to include clinicians in the loop for continuous model improvement with human biases in mind too. We also need to communicate uncertainties and biases of the trained model.
Okay, so you were listening to all the user studies that we were presenting. This brings us to the last section, and let me just play the slides.
Hello again, this is Daby, and let me share a few closing remarks as we wrap up this tutorial before inviting you to a Q&A session. So we covered a lot of ground in the last few hours, starting with a discussion on the current state of AI in healthcare and associated challenges, focusing on the need for ways to promote trust before diving into explainability methods and applications in healthcare from the perspective of several personas. So as we wrap this up, we turn to several highlights of a pretty recent workshop co-hosted by NIH about machine intelligence in healthcare, showing how actually the findings of this workshop are quite aligned with what we covered in this tutorial. So as shown on the left-hand side of this chart, while focusing on arguably the most challenging persona, the clinician, so highlights from this workshop provide an interesting framework for the different methods needed for AI in healthcare, many of which we covered in this tutorial. And this includes method explaining the processing of data, may it be interpretable surrogate or proxy systems used to explain how an AI is processing data, techniques highlighting inputs responsible for an output, visual analytics explaining the output of an AI system have also been discussed. We also talked about systems able to generate rationals. And so these methods are all grounded using a plethora of AI algorithmic classes that are shown on the right-hand side of this chart. And this includes feature importance techniques that we talked about, instance level explanations, uncertainty modeling, temporal explanations, or even transparent or inherently interpretable modeling approaches. So we truly hope that the pace of research in this field in healthcare will be sustained, which will help close that gap between the end users and these AI methods. And this we surely need it, and we're hoping that this will help unlock the power of AI in this industry, yielding to, in general, just better outcome for patients at lower costs. So we warmly thank you for your attention, and we would like now to invite you all to take part and meet us in a Q&A session. Thank you very much.
Okay, so you were listening to our whole presentation. Thank you for sticking with us through this whole period. It was exciting for us to prepare this for you. We actually learned a lot in our thing by preparing this. So on your screen, you see all of us in one insert. And so the QR code, you can also scan that, and otherwise go to our website. We will be posting our slides, and we will be hyperlinking the recordings that are already available in YouTube. So yeah, so I think we open the floor up for any questions at this moment, and feel free to unmute yourself and ask directly if you want at this point.
Hi, this is Prasanna speaking. Can you hear me?
Yes, we can hear you.
Yeah, thank you. I think it was a wonderful session and a wonderful introduction to the topic, and a very useful topic. I work in healthcare and some of these problems. So one question I had from a technical aspect is, when do you think explainability starts making sense in terms of the amount of data available, the density of data, and the ways the data is generated, meaning like clinical data, the features of clinical data are generated based on clinical knowledge first, whereas when you look at image data, the features might have different aspects, like color and other things, but it is not entirely focused on the end goal. So what are your comments on when does these explainability models start making sense, or what is the kind of data you need to have to start applying some of these methods?
Great question. So I'll maybe pick this on, and maybe anyone else on the tutorial panel, please feel free to jump on. So yeah, I think that's a great question, and I think when explanations are required, I think that kind of goes to our main hypothesis for this tutorial, which is it depends on your use case. So let me clarify my remark. So as you mentioned, right? So you mentioned images. So it depends really, like, where is this getting applied to? So in the very simplistic use case, let's take clinical image analysis. Let's say we are doing radiological analysis. In those cases, even though like the general body of images is quite large, medical images are usually not that big of a corpus. But for them to be applied in real world use cases, so when, for example, your radiologists are using them or your doctors are using them, explainability is definitely a requirement, right? So you need to kind of point out that here is this subpixel that indicates there is a tumor, right? Or I was attending this wonderful talk on COVID yesterday, and so there someone may be looking at MRI images of various organs of the body. Someone may be looking at the lungs, and you may want to actually find that the model is looking at the blocked pathways between various ventricles in the lungs, right? So, and if a model then says that, okay, there is something going wrong in this patient's lungs, that is more relatable, right? So definitely, I think the main hypothesis that we say is that it's a requirement based on your use case, like whether it's high stake decision making or not. So saying that, I do want to point out like one thing. So here is an alternate viewpoint for the requirements for explainability, right? So people kind of point out that airplanes, we pretty much know that they fly. Their aerodynamics are pretty much, we know that in this kind of wing shape and those, they will fly accurately, right? But we don't exactly know how how that system works. There has been the fluid mechanics flow is still a active area of research, right? So why is that not a requirement? And so there has been some viewpoints, right? And I would actually point out to some of the very nice, there is a nice articles by Hamza and so on, where people kind of point out that if there has been a repeated manner in which a system has been able to demonstrate that they are predicting the right thing, the requirements for explainability kind of goes down because people start to build inherent trust in the model. Many of the applications, the novel applications of machine learning and AI that we are seeing, so they are still at the stage where they are not in the, let's say, the gold standard of like random control trial. And that's why to get us to that point where we can trust these models in high stakes situations, we need explanations. I don't know if anyone on the panel wants to jump on that.
Thanks, Prithwish. I just wanted to add something very brief that I think quantifying the uncertainty also is very important. So even if you don't have a lot of data, the model should be able to provide some insight to the end user on how certain or not it is. And that's a component of explainability that we see in healthcare being very relevant. Physicians want to know these things. Just wanted to bring that up just to complement what Prithwish just said.
Yeah, just to add on to that, can you guys hear me?
Yes, we can.
Yeah. So there are also cases where, like you said, the pixels thing, right? But there are now, firstly, quite a few image data sets coming up with like high level attributes. So for example, there's deep fashion, there's also celebre and stuff where besides the images, you also have attributes like, does the person have a mustache? Are they wearing lipstick and so on and so forth? And also even certain sort of, I think, melanoma data sets and so on and so forth. So the thing is that although your classifier may be built on pixel level thing, your explanation models can try to actually explain at that level of abstraction where does the feature actually have some semantic meaning. So you don't have to explain at the pixel level. So actually the CM method that was presented, we have some extensions and which is also available through the actually X360 toolkit where you can use such high level features. And the other way to get such high level features is also there is this work going on called disentangled features. So there's a lot of work on manifold disentanglement where even though you're given some like images where like pixels are not really humanly interpretable, so you try to actually extract higher level features from it. And like I was saying, in the melanoma data set, you can actually extract certain high level features, and then using those features, you can, obviously the method doesn't know what that feature means, but as a human, if you take that feature and keep all the other features constant and just shift that one feature, you can actually, for many of such features, you can actually sort of semantically tag them. And then once you semantically tag them, you can actually generate explanations at that level. So there are other ways where even though the model might have been built on some other feature space, which is the original pixel feature space, you can actually generate explanations at semantically meaningful levels. And yeah, I mean, I can share like one of our papers if you want, if that helps for this. But
that will be great. I think all three explanations were really insightful. Thank you for that. I know I'll have more questions that are popping up, but I'll leave the floor open to others. Thank you so much. And if you can share those papers and slides, that would be great.
Yeah, I'll just put it on the chat. Sure.
Okay, thank you. The great question to start us off. And so we just to also remind you, we will be like while we may not be live for other sessions, but you can also use the vFace chat or the Hova chat, whichever is the easiest throughout KDD to ask us questions, and we will be pasting some of these on our website as well. Okay. Anyone else?
Hi everyone, this is Srinivasan. Can you guys hear me?
Yes, we can hear you.
Okay, great. So I had a question around the effectiveness of these explainability models when you have some sort of a skewed data set in terms of class imbalance. So if your positivity rate in itself is very small, which is pretty common in the healthcare domain, how would these explainability methods fare?
Yeah. So that's another great point. I think I was just having a discussion with someone else on this feature, right, of healthcare data. It's most problems that we study are highly skewed, right? So I think there are a couple of ways to look at this. So let's start with maybe like a self-interpretable model, right? Or some models from which explanations are easier to extract. Once we have those, you could actually use them to debug your model, just to make sure that the main concern with these kind of imbalanced data sets is that you're not really learning any discrimination, right? Because the average is so high. So you could start to use this kind of explanation methods to debug, right? Uh, However, saying that, right, so I think when you're starting to do some kind of like post hoc model explanations, depending on the method, they can still be susceptible to their outliers and their class imbalances, right? So that is quite possible. And then so my guess is it depends on the method. So for example, one could start applying similar kinds of techniques people use for imbalanced data sets when they're also trying to learn the explainer methods. Uh, Anyone else on the panel that want to pick on that?
Yeah, I think Prithwish, I think I completely agree with what you said. I think that makes complete sense. Yeah, I mean, I think even for imbalanced data, they could be applied in similar ways. So, for example, like in CM, I mean, there is one guarantee that like if you find pertinent positive, which is basically part of the input that lies in the same class, it is guaranteed to lie in the same class as the original input. And if you do find a pertinent and negative, it is guaranteed to lie in a different class. So there is that guarantee. So that the classifier will, with 100% guarantee, classify it in the same or different class. So even if the data set is unbalanced or whatever, it may be harder to find such points if say they're trying to find for some outlying class. But uh, if things are found, it should have that kind of guarantee. And even with some of these proxy model based methods like Lime, for example, it anyway just takes your input and perturbs it, and basically it's like creating its own sort of local data set. So even if it's highly imbalanced, if you know that classifier is doing well, since it does that this at an individual point level, it should still be able to sort of generate some kind of explanation that's as reasonable or as you have a balanced data set.
Okay. Yeah, that makes sense. Thank you.
Yeah, thanks for the question. Okay.
This is Prasanna again. I have one more question. Explainability, is very useful. I understand, especially in healthcare. How do you go from explainability to kind of actionability, in the sense that if I'm predicting the risk for someone, and I say, okay, for example, this is a 65-plus-year-old male with some conditions. It is a very valid explanation to the physician, but the physician cannot intervene on age and gender. They need features that can be intervenable. So how do you balance in any of your use cases that you've come across? I know there are two different problems, explainability and trying to come up with features that are actionable. But how do you balance that, or how do you address those problems?
I feel like that's a great question. I feel like there are many people on the panel who are itching to bounce on that. So maybe I'll let others take a first stab.
Yeah, let me start this. I'm sure we're going to discuss among ourselves. My first take, this is Daby. My first take is that these are, as you said, these are two different problems. When we are learning maybe with a surrogate model or all of those techniques that you saw in this tutorial, especially the model agnostic ones, they're trying to explain what the AI did. They are not necessarily modeling the underlying causal structure, which is what you need to get at actionability. So in a way, if you have an algorithm, if a CM algorithm is telling you that these are the pertinent negative and the pertinent positive, this is trying to get into the head of the AI. This is how the AI is looking at those features. But there's a leap to go from here to go all the way down to say that this is the actual causal phenomena. If you want to get at that level for actionability, I think we're starting to cross the boundaries towards causal inference and this type of techniques, which comes with its own challenges. Let me pause here. I'm sure others may want to add to what I just said.
Right. I just want to, as you said, Daby, completely agreed, and just want to add to that, right? So, I mean, and this is an experience that many of us, we work with healthcare data day in, day out, and we of course find this, right? So, as you mentioned, like the explainability is based on like what the model is looking at, right? And as you pointed out, not everything is controllable, right? Not everything is actionable. You cannot control the age of a person, right? So that is a problem. But I think I want to say that's why there is two important things. At the beginning of the tutorial, when we were looking at what is explainability, which is a slightly convoluted definition, but I think we stressed on the need for interdisciplinary approach, right? And I will use this as a segue to mention, in most of these real world applications, you need to work with the domain experts to first of all identify what are their needs for the explainability, right? So for example, in this case, if the doctor is trying to improve the prognosis of a patient, to them, the age and gender, it's good to know, and they would, and I mean, it's still good to know because some of these are linked with risk factors, but it's not controllable to them, right? So in those cases, there are techniques. I'm sure Amit is itching to mention some of those techniques here, but you could, it could be an iterative process, right? So you could find out what the model is looking at. You have your conversation with your domain expert, look at what are their requirements, and then narrow down on the features that they're interested in. So it can be an iterative process. Amit, do you want to maybe add some of that to about the features for MSEM?
No, I completely agree with you, Daby and Prithwish. Just a small thing to add is that, yeah, there's no way that it's going to discover for you, like Daby mentioned, like causal features. But say, for example, like the example of age, right? Like you can't change. But if you know, for example, in your input features that some are actionable, with slight modifications to the algorithm that exist, you can actually force them to only look at those features, those subset of features. So if the feature doesn't lie in your input feature set and you have to somehow figure it out like some confounder, then these things won't help. But say you like the age thing, you don't want to change. You can with I think with yeah, I mean not think. I'm pretty sure. So with a with some kind of wrapper where you just tell it that okay, don't focus on these features, but like for example like CM where you want to change a feature, like you can't change age of a person, you can't make them younger, for example. You can tell it that okay, like find me a PN that is basically something that lies in a different class, but focus only on these features which someone has basically identified to be actionable. So the algorithms can be modified to this certain degree where you, if the set of actionable features that you're interested in are already a subset of the input, you can essentially restrict those algorithms to only look there. Even for Lime and all, you can do that because you can just essentially fit the proxy model just based on those features rather than everything else.
Yeah, thank you. I think you cleared my thought. I mean, I'm in agreement with all of you. That's what I thought, that these are focusing on explainability, and actionability is a different problem, more related to causal inference. But I also like the explanation, Amit, you gave at the end, is we could try out with using features in our input data space that we know are actionable, and kind of give weights to them to see if we can use them for actionability while not reducing the overall. I guess we have to be careful that we don't reduce the overall explainability because if you drop age and gender, then explainability might go down as well. But if it doesn't, yeah, to kind of try out some of these experiments is a good idea.
Yeah.
Thank you.
Yeah, I think for special, no, so what you could do is like, maybe run, but like, if you just want to highlight important features, you can keep your age. But things where you want sort of, oh, if I change this, what will happen? For that portion, you can basically tune out features that you know for sure like can't be changed. So, so you could have sort of in a certain sense best of both worlds.
Yeah.
Thank you. Great insight.
Yeah, in that case, you may still run into unobserved confounders. If you have things that are unobserved, you have to be careful. So it's a, yeah, I mean, it becomes it's really a causal inference problem. Yeah.
Thank you, everyone.
Okay, some great questions. I'm happy that this session is getting recorded. So we'll work with KDD to see how we can make this recordings available. But yeah, great discussions going on here. Okay. Any other questions, thoughts, feedback?
In terms of feedback, I think it was very well presented and very useful and structured. I really liked the tutorial. Yeah, thanks for putting this together. And I think it's an important topic that is gaining a lot more traction and a lot more work needs to be done in this space. But thank you.
Yeah, thanks. Thank you.
Yeah.
Okay, so I think it seems that we are almost at the end of our questions. So just wanted to again thank all of you for sticking with us together. I last checked there were about more attending than also on the Zoom link. So as feel free to drop your questions on Whova, on vFairs, or just contact us directly, whichever is the easiest. And yeah, so hope you enjoy the remaining parts of the KDD. It was good to just kickstart today morning. And yeah, and so we will be uploading all of the slides to the website soon.
Thank you very much. Thank you, Prithwish. Thank you all for attending.
Thank you, everyone.
Thanks.
Thank you.
Thank you, guys.
We are going to stop. Thank you. We're going to stop the screen share and we'll be closing the meeting in a minute or so.